Okay, this is number 4 in your book, and I went ahead and just started the pink part, which is a very elementary uh, part. So here's our given differential equation in white, and we want to write it in our standard form. So again, I just divided both sides by 3x cubed, and then I obtained the following. We have our p of x, and we have our q of x. So let's go ahead and take the limits. So the limit as, and this is going to be my, actually let's just write down p naught, and that's going to be the limit as we're interested in as x is approaching 0. And again, it's of p of x from the last video. It's erase that. Let's write it as it's x times our p of x, right? And this is, this whole together, we call that little p of x. Okay, so if we compute this limit, well, let's go ahead and insert a couple of things. So we have, x times a p of x, a capital P of x, which is just 2/3 x, and this one's not too bad, right? That's just a 1, those divide out. So the limit as x approaches 0 of 2/3, well, that's just 2/3, right? The limit of a constant is a constant, right? Because this function here it's just a horizontal line, right? Pretend this line is 2/3, right? As x is approaching, here's obviously 0. Ignore that one actually. If x is approaching 0, the limit is always going to be 2/3, right? At any, it's always going to be 2/3, but specifically at 0. Okay, so that one is fine. This is finite, right? The limit definitely exists, and some students just want to. I want to do it quickly, just in another way, because it depends on the student, the preference that they'd like to approach this by. So what I did right now, okay, we found the limit. That's fine. If you remember in the last video, I wrote y double prime plus little p of x over x, y prime plus q of x over x squared, y equals 0. So you should have that in your notes. So we had this guy, and then we can transform it into this guy. Now, if you want to work with this guy, this is fine. But this is nice as well when you see an x and you see an x squared. If you manipulate the equation to make your denominator x and x squared, then, you're really just taking the limit of little p of x. So, for example, if you wanted to, let's see, okay, so I'm talking about this guy here. If you want it, we know we can write 2/3 x y primes. I'm just getting that piece. Right, I can rewrite this as, I can make it look like this, where, this is really just 2/3. Let me move this a little bit higher here. Okay, so this is really 2/3 divided by x, right, with y prime, of course. So my little p of x, okay, let's, colors here, green. Okay, my little p of x, so this guy, right, that p of x, that's really this guy here. So, if you take the limit of, as x approaches 0, of 2/3, let's do 2/3, then of course you get 2/3. Some students don't want to do this part. It's really up to you. If you're comfortable manipulating the expression so that it looks like this expression where you have x in the bottom and then you're just taking the limit of your little p of x, that's completely fine. And then you can do the same thing with x squared. So again, you can do this part, right? Or you can do this part. I mean, you get the same limits. Okay, so Q naught. So Q naught is, well, let's do it one way first. So the limit as x approaches 0 of little q of x. Okay, my little q of x is really x squared times capital Q of x. Okay, so let's go ahead and do it the first way. If we have, okay, so we have Q naught, so the limit as x approaches 0, and then I'm using this guy, so x squared times, and according to our problem, what was Q of x from way above? And it's this guy right here, right? 1 minus x squared over x cubed. So I have 1 minus, oh, that was it, 1 minus x squared over, I think it was 3x cubed. And then here, you know, students like to just simplify this a little bit, right? We know x squares are gone and we're left with 1x. So we have this rational function, right? This guy, I mean, if you graph this, it's a rational function. And you can use your graphing calculator, obviously. And if you graph it, right, it's a kind of funky graph, right? You can zoom in as well, right? It goes like this, right? And then at 0, it kind of gets a little crazy, and then it comes back up. And as x approaches 0, it actually doesn't, it's, if you want to explore on your calculator, which I encourage you to do, you know, if x is 0, you know, your calculator will say, oh, y is, you know, about negative 0.96. And also when x is 0, y is, you know, negative 1.29, as it, right, it changes here. I mean, you can't really see it in my picture here. I mean, it's nicer on the graphing calculator if you want to graph it using Mathematica or Maple. You don't approach, I mean, the limit is unique. It has to, as x is approaching 0, we have to approach one specific value. And here we were getting, you know, more than one value. So here the limit actually doesn't exist, so does not exist. So again, this is one way you can approach it, and again, use a graphing calculator. If you want a more algebraic approach, well, I mean, we did use algebra, but you can also say, so Q naught, right, we also know is Q of x. Okay, so let me go ahead and write that again. The limit as x approaches 0 of Q of x. So instead of writing this guy, what is our actual Q of x? So we go back to our big Q of x, and let me move this down a little. Okay, so I'm looking at this guy here, and I would like this to look like, okay, so here's, whoops, right, there's my Q of x, so hopefully you can see my pointer here, and there's my expression here, right? I have a little Q of x. So can I, you know, maybe manipulate this so that I only have x squared in the denominator, and then whatever's left over is my Q of x? And I mean, we can do that. We can rewrite this as, let's see, we can say 1 minus x squared, and this is just using your algebra skills, over 3x. I mean, that's really the same thing as times 1 over x squared, right? I mean, multiplying fractions. And, I mean, we can even write this as 1 minus x squared over 3x divided by x squared. Because, right, when you divide by x squared, I mean, when you divide by x squared, you're just multiplying by the reciprocal. So this is my nice, here's my Q of x. And again, it's your preference if you're comfortable manipulating the expression. So my Q of x is 1 minus x squared over 3x. So 1 minus x squared over 3x. so 1 minus x squared, right, it's my green, over 3x, right, because it's in the form, again, where our denominator is x squared. And if you try to take the limit of this guy, again, this is great. Now you're just using more calculus. If we try to take the limit of this guy, I mean, usually, again, direct substitution. If we try direct substitution, we get 1 over, what? Well, 3 times 0, which is 0. So 0, I mean, we can't have a 0 in the denominator. It's not defined. So then, I mean, you can say here that the limit, of course, doesn't exist. So it's the same idea here, right? Something very weird is going on when x is 0, which clearly it is from your. And again, I really encourage you to graph that that function. We're doing the math, but it's very important for you to see the graph as well. Okay, so I mean, we did get a limit. We did get 2/3 for P naught, but for Q naught, the limit didn't exist. So that's, I mean, one of them already fails. So here, we can even say, let's just practice our terminology. Since Q of x, right, which is that right there, is not analytic at x equals 0, then, of course, x equals 0 is a irregular singular point. And since it's irregular, then there's no need to find, there's no exponents using the initial equation. So that's pretty much it. Again, it's not analytic. You can also say, since the limits are, well, one of the limits doesn't exist, it can't be regular singular, because in order for it to be a regular singular point, both P of x and Q of x, little p of x and Q of x, have to be analytic, and of course it fails here. So that is example or number 4 in your book. Hopefully that makes sense.